Hello, everybody. It's Mrs. Pound, and we are finishing today's the chapter today on waves, chapter 6.1. This is a really short chapter. So, what we're going to talk about today are wave behaviors from section 613. And our objectives are to examine the 5 basic wave behaviors, differentiate between refraction and diffraction, and apply basic wave behaviors to real world examples. And I will be demonstrating all of these wave behaviors for you in class. So the first one, which is probably the most familiar to you, is reflection. And this is the bouncing back of a wave after it hits a barrier that does not absorb all of its energy. Now, generally, what happens when a wave hits a barrier is it can be reflected, or it can be absorbed, or it can pass through. And so, even on the surface of this pond or lake, this body of water, we can see the reflection, but some of the light also may be passing through and maybe being absorbed. So just be aware of that it's not just 100% reflected. But the reason you see this tree is because it is bouncing back. This is what's happening in a mirror when you see your image, okay? Okay. Now, the law of reflection states that the angle of incidence is equal to the angle of reflection. That means the angle that the light comes in at is the same as the angle it reflects at. And I have a billiard table in the background with some billiard balls on it because that's exactly how the law of reflection works, is just like billiards or marbles or anything like a ball that reflects. You've probably noticed the angle that it goes in at is the angle it comes off at. And so it works with waves the same way. So here, what it means by the incident ray, the incoming ray bounces off at the same angle as the reflected ray. Now, the normal is parallel to the mirror surface, and this angle here is equal to this angle here. So the angle of incidence is the same as the angle of reflection. That is what they're talking about. And so you could even see this with, say, if you are playing pool, the ball comes in, it bounces off the wall at the same angle it bounces over there. If you play basketball, you use this for a bounce pass. You have to calculate that by practice, those angles. Now, light can also, or waves can be absorbed. Absorption is the conversion of a wave's energy into another form of energy. So in this case, it is light. So white light is coming in. Now, white light is made up of all the colors of the rainbow. So white light comes in. Green light reflects. That's why a leaf looks green, is because the green light is reflecting to your eye. All of the other colors are being absorbed for use by photosynthesis. Also, you might notice this with light as well, that if you leave something in the sunlight, let's say you leave a shirt in the sunlight, let's say it's a red shirt, you will see the red, but when you touch the shirt, it will feel warm because it's absorbing all of the other wavelengths of light. And you also should notice that when you place something that's white versus something that's black in sunlight, the white will feel cool while the black feels very hot. White is reflecting all of the wavelengths of light, black is absorbing all of them. There's also refraction. This is the bending of a wave because of a change in the wave's speed as it passes from one medium to another. This happens with a prism. This is where rainbows come from, because the different wavelengths of light, each color has a different wavelength, and when they pass from one medium to another, from air to glass, they will actually bend, but they don't all bend at the same angle because they're at they will bend at different speeds. They will go at different speeds through that. So that's what is happening there. Also, in a glass of water, if you put a spoon in a glass of water, it will look like it gets cut in half. That is due to refraction. So if you're listening to this video, next to refraction, draw a rainbow. There's also diffraction. This is the bending of a wave around a barrier. And so we can see here around these islands, kind of if you can see in the background, like right here and things, um, all of these waves are bending around these landforms in different directions. This is due to diffraction. And an example is I can hear sound from the hallway at my desk. If sound waves did not bend around the door, I would only hear the sound waves if I was standing right in front of the door, which they are most intense in front of the door, but I can also hear things from the hall at my desk. So, likewise, you can hear the cheers of stadium fans in the tunnel before you can see them because sound waves can diffract around the edges of the tunnel. Light waves cannot because they have shorter wavelengths compared to sound waves. So sound waves diffract, the light waves will not. And the final thing I want to talk about is interference. This is the effect produced by the combination of two or more waves. We can have constructive interference where the waves match up and they build and they're more intense, okay? Or we can have destructive interference where they don't match up. So this is where crests and troughs match up. This is where a crest matches with a trough and they actually cancel each other out. This is how noise canceling earmuffs work, okay? And you might find if you're sitting in a theater somewhere sometimes, there are dead spots. There are spots where you hear the sound really well. There would be constructive interference going on there. And then there are dead spots where you can't hear very well, and there's destructive interference going on there. Now, with this idea, we have what's called an antinode. This is the place where constructive interference causes the largest wave. And so the antinodes are right here, okay, with our constructive interference. And I'm going to be demonstrating this in class for you. And then we have our nodes, excuse me. The node is where destructive interference causes node displacement. And so nodes are right here. And I'm going to demonstrate this for you with a slinky in class so that you can clearly see this. It's also the idea is stringed instruments have nodes and antinodes as well. So our objectives were to examine the 5 basic wave behaviors, differentiate between refraction and diffraction, and apply basic wave behaviors to real-world examples. So don't forget your 5 questions, and this is it. You can start studying for your test.